And now we will start the technical program of this event. So the very first talk is by Ali Sheikholeslami from the University of Toronto. Ali is also the organizer of this event. So if you see the names of the speakers, so Ali was basically contaction and inviting all these wonderful speakers. So Ali is a professor of electrical and computer engineering at the University of Toronto, Canada. And his current research is in the area of integrated circuits for wireline communication and the optimization. So he currently serves as the education chair of the International Solid State Circuit Conference and the vice president education of the Solid State Circuit Society. He writes a regular column in the Solid State Circuit magazine titled Circuit Intuitions. So in the very first talk, Circuit Intuitions is Ali. Okay.
Good morning, everyone. Thank you very much, Alina, for your kind introduction. And I would like to also thank the ESSCIRC chair and, of course, the SSCS president, John Long, for bringing us together and for sponsoring this event. So thank you very much for doing this. And, of course, thank you all for filling this room. It feels really good to be with you today. As Alina mentioned, I'm going to talk about Circuit Insight today. And, in fact, one of the fun activities that I have for myself is that I write these regular articles that show up in the Solid State Circuit magazine. As one of the benefits of being part of the SSCS is that you can get those for free, is write Circuit Intuition. So this is going to be essentially the topic that I'm going to cover in this 1 hour that I have with you. But before I go and delve into the Circuit Intuitions, I would like to give you the bigger picture here first. The bigger picture is about what we are doing in electronics and in circuit design. So if somebody asks you today, what are you doing in the electronics, we tend to go to applications right away. You can say that we design computers, or we design microchips, or we build cell phones, we build cameras, we build whatever that has electronics in it. And this is true, of course. We are doing all of that. But what is that we're really doing? What is common among all these applications? And this is the big picture that I want to share with you. What we're really doing is that we're controlling electrons. This is what electronics is all about. Electronics is the art of controlling electrons. And we are controlling electrons for at least several reasons, but the most obvious ones are the following. We control electrons for the purpose of storing information. When you're storing a bit, a single bit, into your computer, whether that is a picture or somebody's voice that is made of bits, that storing of bit is equivalent of controlling electrons. How do we do this? In this case, when you're looking at a single DRAM cell, you have a capacitor. Either you charge it up with electrons or you discharge it from electrons. So essentially what you're doing is that you're using this device, which is a transistor, and you use it as a valve to pour electrons or charge into this capacitor, and then you disconnect it. So you're controlling electrons movement. You pour electrons, you store them, and then you hope that it stays there for a while, and that is how you store a 1. But of course, over time, as we know, these electrons or charges are going to leak through this transistor, and then of course you have to do more for them. So what are we doing really? We are really controlling electrons to store information. We're also controlling electron to process information. Information is the same. We're dealing with bits. But what we're doing here is, for example, you have a signal that represents your voice perhaps in analog, and then you need to filter it. And this simple filter is essentially getting rid of the noise. because our voice usually has lower frequency, but there may be some noise involved and you like to get rid of it, and you can process it using this. So what are we really doing here? Well, it looks like at the math level, we are taking this and we multiplied it by this Laplace transform and we get the output. But in reality, we're using resistors and capacitors to do this. And what we're really doing is that we're creating electrons corresponding to this x of t. There's a voltage corresponding to this. And this resistor is resisting the movement of electrons, and the capacitor is going to charge and discharge. And essentially, we are, again, controlling electrons in order to process our information. We also control electrons in order to communicate information. Whether it's your cell phone, you're talking to someone else, whether it's wireline connection between the two things, or wireless, what we're really doing is that we're using a power amplifier here, that's the circuit, and we're controlling electrons in order to build the right voltage or current for this antenna. This antenna will send a wave, and the received antenna will take it, and will control the electrons again in order to get the data that we sent at the transmitter. So you can see in all of these, this is the common element. We are really in the process of controlling electrons. So that's really the big picture that I wanted to mention to you. But what is interesting is that the center of these controlling electrons is circuit design. So if you look at this image here, circuit design, that means hopefully all of you are sitting here at the center of this universe. Circuit design means that you are going to use elements such as transistors, resistors, capacitors, inductors, and you build things to control electrons for the purpose of one of the things that we said. Now, as I will mention to you briefly, and you'll see it through the team today, dealing with one circuit, one element is easy. You can just write the equations, you can get it to work, and it's all good. It's only when you get many of them, you get thousands of transistors, and then you will get the situation where these transistors are having their own individual characteristics. We intend them to be identical, but there is a random process involved. And then how do you make sure that at the end of the day, when you make tens of thousands of these transistors, that they will work what you want them to do, that they follow the same equation that you had in your mind? That is the art of designing electronics in this case. Now, once you have these electronics on its own, and I can tell you, electronics on its own is a very beautiful set of concepts and ideas and understandings, but then you can use them to build stuff with those. And that is when, for example, you can go and build sensors. When you attract or you take light from the objects that is coming to you, and then you would use electrons to control how to process that information. That becomes sensor circuits. Or you go to systems control. Take, for example, a car, and then you're dealing with various things that you need to make it efficient, whether it's a cruise control, whether it is the noise that the car creates and you want to reduce it. All of these are going to be controlling electrons for the purpose of controlling a system. In communications, I already mentioned to you that we can use an antenna and send signal from one point to another and be able to do this without much error. You go to machine learning and AI. This is a huge topic today. And of course, machine learning and AI, at the surface, maybe you're dealing with the software, but underlying hardware is all circuit design, and it's all about controlling electrons. You go to quantum computers and say, here's where we can stay away from electrons. But no, don't go too fast. In fact, if you look at quantum computers, look at a quantum state of even an electron. That's what we're trying to control. We're trying to now control the quantum state. But how do we do this? We use electrons to control electrons. Even when you go to photonics, you use light. Today, we're using electrons to control photons. So it's all about controlling electrons. Now, I guess we are very lucky today, in fact, to have all these topics covered that I just mentioned to you. I'm going to talk about basics of circuits, maybe at a very low level, and provide you with some intuition. I would just want to make sure that you understand that circuit design is fun and is absolutely easy. And I can make a claim here. If you come and tell me a circuit is difficult, I just tell you that you probably do not understand it, because that is my measure of how things are understandable. You understand something when it's easy. If you think it's not easy and it's difficult, it just probably means that you don't understand it. And by the way, we do have many difficult concepts. I have it in my mind. I've written them on my to-do list to make them easy for myself later. And they will become circuit intuitions, hopefully another time in the future. When I finish, then Kofi, who's here with us, he's going to talk about these non-idealities, process variation. He has a magic of looking at multiple transistors that are built all with different imperfections, and he somehow makes them together and uses his power of averaging to make it work. So that's going to be the second talk that you're going to enjoy today. And then we go to sensor circuits. Sarah is going to talk about circuits for sensors, and I think you will see exactly how she's controlling electrons in order to build great sensors. And then we go to automotive, and this is Javier is going to talk about the cars and the noise and how we can control, how can we make better engines which are far more efficient by using electrons to control these things. When we go to communications and we talk about 5G and 6G, and this is Stefan who is going to talk about this, then we go to machine learning, and this is Mahmoud who's going to talk about machine learning and how we use circuits for this purpose. And then we go to Andrea, who's going to talk about quantum computers. So this is really an overview of the whole day. But remember, in every one of these talks, I would like you to ask yourself at the end, where am I controlling electrons in this area? For what purpose? And you can see, hopefully, that it will follow one of those three categories that I mentioned earlier. I said that when you design circuit, if it's just one or two transistors, life is easy. It actually reminds me of my own childhood when we were trying to build Legos. And in the old times, and some of you in the audience may remember those times, we only had one type of Lego. It was a single brick, and if you were lucky and you had the money, you can buy different colors for them. And with that, of course, you can build this delicious watermelon piece here on the right. This was the old time. And then you bring it to today, and now my son and my daughter are playing with this. This is the real life here. If you Google it, you'll find out today there are more than 1,300 individual pieces of Lego that you can access. And with that, you can build this giant ship on the top. You can build the structures, castles at the bottom, or build bridges. Things are far more complicated than it used to be. Believe it or not, the same story goes for our circuit design. We used to have just the CMOS transistor. It was 0.8 micron technology. You make an amplifier, 2 transistors, you write all the equations, you drive everything from beginning to the end, you analyze it, you measure it, everything would work. But then came, well, maybe thresholds shouldn't be just one value, the standard. You should have low threshold, high threshold transistor, then ultra low, and then ultra high threshold. And then it could go to, in the last few years, go to FinFET. And you remember we talked about controlling electrons? When you're controlling electrons using a planar transistor, you just have a gate that is sitting on top of silicon, diffusion, and is controlling electrons that are moving underneath. But then we felt that's not enough control, right? This is not enough control. What we should do is we should go and surround the area of diffusion so you have better control. And that is when the number of variety of transistors on what you could design exploded to the point where today you look at the transistor, the number of parameters that will characterize one transistor are in the hundreds. In fact, if you look at the layout, that if you want to do layout, and some of you in graduate studies are doing this, you find out the number of, this is design rule checking documents that you get from the foundry. In order to design anything, it's over 1,500 pages of PDF. 1,500 pages, and it's just the rules that if you're putting your one layer at this way and the other layer, the distance between them should not be more than this. So it's huge numbers, and it's just very hard to imagine how you're going to design in this environment. And this is what brings me to the concept that I like to explain to you, and that is circuit intuitions. So in summary, what I said so far is all motivations. What I'm saying is that there are many barriers to entry when you look at circuit design. From high school, when you go to first year university, the first thing that you find out is that designing with these tiny devices that cannot be seen or touched. When you talk about the transistor, we're talking about these days few nanometer. I don't think even the microscope that I have at home can show me what that looks like. We just have a schematic, we make it big, we'll see it, but you can never see it. Even, of course, electrons. We say we want to control electrons, but you've never seen one, right? I'm sure you've touched it, but you've never touched one. You've just touched thousands of billions of them at the same time. And then we're going to use electrons to control electrons. That's even more complicated. We're dealing with these abstract concepts. It's not mechanical engineering when you have a pipe you can imagine, you can see it, you can touch it, or you have a water fluid that you can deal with it. It's electrons, and you have no way of feeling close to it, right? Even though you're immersed in it. The formulas become too large all of a sudden. If you should go beyond 5, 6 transistors, good luck writing the equations for these transistors. Just impossible. And hand calculations just takes too long. So it's very easy and tempting for new engineers to say, well, I do simulations. Thank God we have computers. I can do simulations. And they just run simulations. And then they get the output, and is, you know, what we call it, garbage in, garbage out. You get something. You don't know if to say, well, it shows that it works, but I don't know if it works or not. And it's interesting because sometimes graduate students, when they design a chip and they go through the entire process, and of course we will make sure that they all work well, they get the chip back. And it's the time to do measurement in the lab. They go to the lab, of course it doesn't work first day, they work for a week and debug it. And then at the end, one day it works, and the guy says, I can't believe it, it works. And he said, well, didn't you design it to work? He said, yeah, but I cannot believe it that it works. It's just two different things. It's just amazing that you think first. Everything is in your head, right? Everything is in your head. You imagine things. And then you build something in the outside world, and that matches your imagination. I think this is the most beautiful thing that has ever happened in our field, that you feel that, you know, you imagine something, and then you're thinking about electrons that you never touched. You imagine how they should work, and you build thousands of them, you know, thousands of those transistors, and they all obey what you said they should be doing. This is the magic and the beauty of our field. So what am I doing here? I'm just trying to say that we need intuitions. In this complicated world, you need to make sense of things, and the things have to be easy to understand. And hopefully, these intuitions will do this. So with intuitions, circuit design and analysis becomes easy and enjoyable. And that is my mission today. So intuition also is an essential component of innovation. How could you possibly come up with something new if you don't understand what's going on? I mean, the old idea, I don't know, Hollywood movies that you just write equations on big board, and then one moment you say, boom, I came up with a great idea. It's just a lie. You have to have intuition. You have to understand the previous art, and you have to feel close to it. You need to know it inside out to the point that you feel this is trivial. Whoever came up with it, this is like obvious, right? Then you're ready to make your innovation in the next step. And that is what's happening after you get your intuition. Okay, so with this, let me now start telling you that what I said. So I've been writing this article since 2014, I guess. I can't believe that it's been more than 8, 9 years now. But these articles are just 2 pages, one concept, one article, and I try to explain it to third-year undergraduate students. So this talk is going to be understandable by anyone in this room who is a third-year undergrad. If you do not understand it, please talk to me. There's a disconnect here, because I target third-year undergraduate students for this talk. And if you're above that level, I apologize. This is meant for third-year undergraduate students, but hopefully you will enjoy it as well. Okay. The first thing I want to do is, these are the topics I'm going to cover. There's many intuitions, but I'm going to cover 3 of them today. So one intuition is about power of analogies. Use them whenever you can. Analogies are extremely powerful. They're not for the weak or people who cannot understand equations. No, you see the equations, you see what's doing, but you have no clue what's going on. With analogies, they become easy. They come to you, and then you feel them. And that is what I like to show you as an example. So whenever you can see analogies work, they work beautifully. Use them. The second one is Thevenin and Norton equivalent circuit. You may say, wait a minute, we thought this is the third year and above. This is like first year we saw. And yes, you started in first year and then you forgot about it. And then, of course, for some reason, the books that come later in electronics, they never mention Thevenin and Norton equivalent circuit. Maybe they don't think it's necessary, but on the contrary, Thevenin and Norton equivalent circuit is going to remain your friend for as long as you work in analog circuit design. So I will emphasize this. And again, there are more than one article on this, but I'm going to give you a gist of it. And you see how powerful they are, especially when we're designing with transistors. And lastly, I'm going to apply this Thevenin and Norton equivalent circuit concept to flipped voltage follower. Just give you an example of how you can analyze things without writing any equations, and just by seeing it, understanding it, hand waving it, and hopefully get intuition. Okay, analogy with a glass of water. So I need to get some water. This is why I pour some water from you at the beginning. So what I say here is that charging up a capacitor is actually very much like filling up a glass of water. And to see this, think about it. If you have a capacitor with capacitance C and voltage V, you can imagine a glass of water with cross-section area of C, same C in terms of value, and water height of V. Now, I claim that this is acting like a capacitor. Let's see the equations and see if this is consistent with what you believe. So the capacitance, as I said, corresponds to the cross-section area. Voltage, which is here, across the capacitor, corresponds to the water height, also V. And then the charge is going to be CV. Interestingly, the water weight here, water volume, I should say first, is C times V. But if you, for simplicity, you imagine rho, which is the water density, is 1, and G is 1, just make simplifications, then you can see a one-to-one correspondence. The weight of this water is also CV, or you can say the volume of the water is CV. Now, what about the stored energy? You have learned this in your first year undergrad. When you have a capacitor, you charge it to voltage V, the energy that you stored in this capacitor is half CV squared. Let's see if this is true for the water. So the weight of the water, we say is CV, because we assume that rho is 1 and G is 1. So this is CV. And what is the center of mass here? Center of mass is sitting at V over 2. V over 2 times CV is half CV squared. So the energy you store in the capacitor is half CV squared. The energy you store in a glass of water is half CV squared. Now let's see what is the process by which we charge a capacitor. We typically use a PMOS transistor, let's say in this case. It could be a switch. I just use a PMOS arbitrarily. So when the gate goes from VDD to ground, you essentially start charging this capacitor. If it was discharged at time equals 0, then you start charging it up with this. And as I said, the energy that you're going to store is going to be half CVDD squared. But interestingly, in the process of charging this capacitor, you also waste exactly the same amount of energy. And some of you may have been surprised by this in the past when you've seen it first time. And then you kind of convince yourself, yes, there's some resistance in this, and probably as you're charging this up, initially you're charging this capacitor and you're storing, but then you also waste a lot of energy here because there's a voltage drop across this resistor, which is VDD minus 0, large resistor, same current. You're going to waste a lot more here than you store here, because remember, the storing and wasting is all V times I. So when you're storing charge here, at the beginning, this is 0. So you have a small voltage, but you have a large current. The product is close to 0, so you're not doing much. But then here, you have the voltage, which is large, current that is large, and then you get this is where you're wasting. When you go to the end, when this is almost charged, now this situation is different. Now current becomes a bit smaller, right? Because you don't need to charge as much, and the voltage difference here becomes small, so then you have less. But then, interestingly, when you do the math, you find out that exactly the energy stored is the energy wasted. Is this the same for glass of water? Let's see. So I just pictorially, I couldn't do an animation here for you, but you can use imagination. I'm going to have an empty glass of water, and I brought this water hose. This is my water hose that comes right to the brim here, and imagine the height is VDD, and I try to let the water go, and I assume that this water comes in the form of these slabs of water that just goes in there. As I charge this glass, or fill up the glass, you see this first slab is going to be here, and it's going to fall to the bottom. At the beginning, this water slab has some potential energy, but I release it. It goes to kinetic energy. It hits the bottom, creates probably some disturbances, right? And then it settles, so it stays here. And now I go and then look at this and I drop this again. As I store water in this, or I store energy, potential energy builds up, right? But then at the beginning, there's going to be a lot of waste of equal amount at the end, actually, to the kinetic energy. So every kinetic energy here is lost to heat because you have water that's splashing around and then it settles. So at the beginning, I'm going to lose a bit of energy and store some energy, but as I fill up the glass, you see this later one doesn't have to fall as much, it's just very close to the surface. So you don't lose as much, but then you store actually quite a bit of potential energy here, right? So if you look at this, you can see that, well, this seems to be, yeah, it's true that as I'm storing energy in the glass of water, I'm also losing energy in the glass of water, and turned out to be exactly identical. You can work it out. You can look at this last piece that is you're putting here versus the first piece. They match each other, and exactly the same amount that you store, you waste. When you pour water into this glass of water, as much energy, potential energy that you store, you also lose exactly the same amount. And so you ask yourself, is there a way for me to avoid losing potential energy? How can I charge a capacitor without losing energy? Obviously, we want to just charge. We want to store energy in a capacitor. Why should I lose? And how can I avoid it? And then you ask yourself this question, and this is the power of analogies. I'm sure if you ask yourself how you can store water in a glass of water without losing energy, some of you may have some ideas already, right? I'm going to show you the answer. I'm sure this is what you're thinking. Instead of having this water at the top to drop to the bottom and create disturbance and lose that kinetic energy, you can imagine the water hose, bring it to the bottom of the glass, and then you raise it as you fill it up. I'm sure many of you may have seen this in bars when they're going to fill a glass of beer. They use the water hose or the beer hose and bring it to the bottom, not to cause foam or disturbance, and you just bring it slowly up. This is how you would do it without losing energy or without creating foam. So does that give you an idea of how to do this with capacitors? We should not keep the VDD, which is your water hose, to the top and then have an empty capacitor. We need to bring your VDD down to ground and then gradually bring it up. And believe it or not, this is exactly the circuit that is known as adiabatic circuit. You can imagine when you're doing it this way of charging with a VDD being fixed, initially your voltage of the capacitor is very low. This is the voltage across the resistor that you're wasting. But then if you go here, I take the VDD and I ramp it up. And if you ramp it up, you start from small. Obviously, I started from the threshold voltage of this so that initially I can start charging up. There's a bit of waste initially, but afterwards, if you're slow enough, the voltage across the capacitor is going to follow VDD, and the distance between these two is be close to zero, and the waste of energy will be just as less. And you are ideally can go and store energy without wasting. Now, of course, this was back in the 1980s or maybe earlier that people came up with this idea, then they realized right away that there's a trade-off. The trade-off is speed. You have to do this slowly in order to reduce the energy. If you want to go fast, unfortunately, you have to spend and waste energy. But if you're willing to go slow, you can remove a lot of waste. Now, I'm going to go and apply these analogies one step further and to two capacitors, but I'm going to speed up a bit because I want to make sure that we have sufficient time for the rest. So you've also seen this example when you have two capacitors, right? One is charged to voltage V, one is discharged, and you connect them together via a switch. What happens is that, well, at the end, this voltage is going to be divided equally, will be half V in each. And if you look at this, you can see that this is easy to see because initially you have a charge on this plate, which is C times V, and the charge cannot be destroyed. It's just going to be redistributed with the other capacitor. So that CV is going to be the total charge initially. At the end, you have 2C because they're in parallel, and if you divide the two, you get V over 2, and that is what you get as the final voltage. Now, interestingly, the energy that was stored in the system initially was half CV squared, because this is zero energy, this is half CV squared. But if you go here, you have half CV half squared plus half CV half squared, and if you add them up, you get 1/4 CV squared. So initially we have half CV squared, at the end we end up with 1/4 CV squared. Again, you lose exactly half of the energy that you started from. And the question is, where does this half go? This half CV squared, it becomes 1/4, so 1/4 is lost. Where does that go? And again, I like to go back to the water analogy. See, I can see it in the water case. Where does it go? So I imagine two glasses, separated them with a wall, imaginary wall, and I put a pipe and a valve at the bottom, and this was initially capacitor charge, capacitor discharge, and I'll let it go. And immediately we'll say, yeah, after a while, this is going to be this. It's clear, right? That's conservation of charge, conservation of amount of water, so you get this. But look at this. Here you had a height of V, here you have height of V over 2. The center of mass now is sitting at V over 4, and even if you have the same amount of water, which is 2C times V over 2, which is CV, but it's sitting at half the potential. And therefore, the potential energy that you get is 1/4 of CV squared. So exactly you lose the same amount. And if I ask you, where did you lose energy here? I'm sure some of you will say immediately that, well, there's a pipe, there's a friction, that is water going through this, and of course this friction is going to create heat. And so you lose exactly the same amount that you lost to heat. And this is correct. But then you say, well, what if I don't have much friction here? What if I just imagine that I have a wall here and I zap the wall? The water there's no friction. What happens in that case? You can imagine there's going to be quite a bit of turbulence before it settles. So it takes longer. It's kind of oscillate. Water oscillates. But to see that oscillation, maybe this is a better image to imagine. If you think about it, you have a pipe, and let's say this pipe is frictionless, and you fill up half of it with the water here. This is one capacitor, the other one is empty. If you let it go, you can imagine that the water is going to oscillate between these two before it dies down, finally because of friction that exists. But exactly this phenomenon is happening. How can I think of this to now explain the original problem? You can see that there's a bit of resistance here, but there's also this momentum of the water that's getting the speed, and that momentum is the same as the inductor. And so this is fully explained in one of the circuit interference article, but you can see that this is RLC circuit. It could have over-damped behavior, it could have under-damped behavior, and that all relates to the ratio of values of RL and C, and you can see that, oh, this is all easy, all understandable, and so move forward with this. All right, let me now take a glass of water and then move to the next topic. So Thevenin and Norton equivalent circuit, again, you have seen it, but just to refresh your memory, at a very simple form, you have any one-port device, linear circuit. It doesn't have to be time invariant, it could be time varying as long as it's linear. It consists of, let's say, elements such as resistors, capacitors, inductors, but for simplicity, I'm just imagining that they have resistors, and you have a bunch of sources, dependent, independent, any of them, but they have to be linear. So if you have those, and then you have a load, and the load doesn't have to be linear, it could be nonlinear, and you connect them together, and the idea is that all of this circuit, doesn't matter how many elements you have in them, can be made equivalent to a series combination of a voltage source and a resistor. In this case, because we only have a resistor. And Norton equivalent circuit says it could be made equivalent to a parallel combination of a current source and a resistor. This is something that you have seen. And just again, to refresh your memory, if you have the original circuit, in order to find the Thevenin equivalent circuit, first you just get rid of the load. The load has nothing to do with this. You get rid of the load, you find the open circuit. This is open circuit voltage here. You measure this open circuit voltage, and then you measure the R equivalent. R equivalent, remember, when you're trying to find the R equivalent of a circuit, you need to zero all the independent sources first. Once you do this, you only have a resistor here, and then you put them in series. If you want to go for Norton, you short this. Instead of opening it, you short this. You get rid of the load again, you short this, you find I short circuit current. R equivalent is the same as here, and you can put them in parallel, and this becomes Norton equivalent circuit. This is true for any linear circuit. Now, when we move up to transistors, the same story applies actually. So if you look at a single NMOS transistor, a PMOS transistor, of course the transistors are nonlinear, but in analog circuit design we are trying to bias them at a point where we're only going to have a small signal perturbation, and during that area is going to be linear. And you have seen, probably remember, if you're a 30 undergrad, that this is the model of a transistor at low frequencies. There's no capacitors shown, just a resistive or low frequency behavior. So you're dealing with this GM, which is called short circuit transconductance. The ratio of the voltage here to the short circuit current here to the voltage here is GM. GMB is due to body effect, and so it multiplies by VBS. And then RO is output resistance. So these are the only three parameters that you need in order to move forward. But I'll also say that in this presentation, I'm adding GM and GMB and call them GM effective. Okay, so that's GM effective. And now let's see what we can do with this and how we can marry this to the Thevenin-Norton equivalent circuit that we have seen. First thing I want to tell you is that this is applicable to the Norton and Thevenin equivalent circuit because these are, again, dependent sources, but they're linear and you have a resistor. So there is a Thevenin-Norton equivalent circuit for this. But what is interesting is that when you put them together, and I call them library element in my class when I teach this, is that if you look at these transistors, you need to get used to looking at transistor and remember that this is a linear element if you're looking at small signal. Remember, for a small signal, we usually ground the VDD, or you have a current source, you open it because you're dealing with small signal and not with DC. So you look at this and you ask yourself, if I have a transistor with a source grounded and drain connected to ground, these are small signal ground, then what is it that I see looking into the gate? And if you look at the previous circuit here, it's pretty obvious that looking at this, you see infinite resistance. There's nothing connected to it. Again, this is a low frequency, right? So it is valid. So looking into this, don't worry. If you see this in your circuit, this is infinite. Just throw it away. It's infinite resistance. If you look at this, you have a source connected to ground, gate connected to ground, again, small signal ground. When you look at the drain, you will see just a resistor. This is a resistor. So do not feel alarmed that you're dealing with a transistor. Transistor is made equivalent to a resistor. If you look at this combination, again, drain is connected to ground, gate connected, you look into the source, and you see this is also a resistance, but it's much smaller, is 1 over GME in parallel with RO. And if you look at it diode connected, again, you see a resistance. If you put a resistor in the source, you look at here, there's still a resistor. And by the way, all of these are Thevenin equivalent circuits of the original circuits because you have no source inside. You see there's no source. When there's no source, you only see a resistor. That's what the premise was, right? The open circuit is always 0 here because there's no source inside. So all of these turn out to be just a resistor. These are all different variations of resistors that you could build resistors with. It only when you add a source, for example, these two are without source. Here you put a source here, like Vn, and once you put a source here, now you can measure the open circuit voltage or short circuit current, and you can write them down. And now you can see that this is a Thevenin equivalent or Norton equivalent, depending on which one you take. Also for this case. Now, you can write KVL and KCL to drive all of this. By the way, I would give this as a cheat sheet to my students. They work with it for a while, and then they will become a second nature for them. They will just write it. But I want to show you how I actually show that this is indeed a resistor. Again, you can write the equations and you can find out that it's a resistor, but my preferred approach is the following. So this is the same circuit. You have this transistor and you have this resistor. I want to show you that this is a resistor. The way I show this is that I say, well, we agree with me that this is a transconductance in parallel with RO. That was the model that we had for it. So if you put this, and then you will make the combination of these two turned into a Thevenin, you'll get this. And this is the interesting part. Even though this element is called GMEROVS, this is actually a resistor. Why is that? Because Vs is the voltage across the resistor here, and they have the same current. So if this current is producing Vs here, is producing GMERO times Vs, so this must be a resistor that is GMERO times Rs. And in fact, it is. These are equivalent. And you can see you have 3 resistors, and you add them up. You get exactly that equation. And you can do this for every single element that I showed you, and this is what I do in my class and in circuit intuitions. You can see it. But the effective thing at the end is that you see, well, this is what's happening. If I have a resistor, and I put it in the source of a transistor, that becomes another resistor, and that resistor is GMERO times RS plus some other values, but this is probably dominant here. So if GMERO, for example, is 10 or 20, what you're saying is that this circuit is a resistive multiplier. It takes a resistor, multiplies it by a value, which is relatively large, GMERO, and I see it from the drain. So that's the intuition that you get out of it, but you see, first of all, it's a resistor, and then you find the value of it. Now, from Thevenin and Norton equivalent circuit comes this very important equation that you may find interesting. If you want to find a node in a circuit, any circuit you have, huge, small, and you're interested in a node, voltage, the way you do this is you short that node to ground. It kind of feels scary at the beginning because you feel there's a voltage at that node. I shouldn't be shorting it to ground. If I do this, something may burn, but don't worry. This is just the exercise, right? Short it to ground and measure its short circuit current, and then measure the output impedance of that node. So zero all the sources, find R equivalent the way you know, and then you multiply these two and you get the voltage of that node. This is the direct consequence of Norton equivalent circuit. You want to find the voltage of this node, and I will show you how easy life becomes. You want to find the voltage of a node? Short it to ground. It's easy to find the short circuit to ground, and then you multiply by R equivalent. Okay, here's the example. This is known as a DAC, digital to analog converter. You have V3, V2, V1, V0. These could be binary values. This is the most significant bit, this is the least significant bit, and if you ratio the resistors as R, 2R, 4R, 8R, called as a resistor ladder, and then you go with 8R, you get V out. And I want to find out what is V out here as a function of these inputs. And you may say, well, I just write the KVL here, right? Because there's no other way. Even though looks like a resistive divider here, but I can't do much about it because it looks complicated. And if I use superposition, it's also complicated because I have to ground all of this and do this. Don't worry, zero. Short this to ground and see what happens. What happens if I short this to ground? This goes away. And the current through here is V3 divided by R, V2 divided by 2R, V1 divided by 4R, VO divided by V0 divided by 8R, and you add them up. That's short circuit current. You already see the DAC action here, right? Because these are being scaled with the binary ratios. And now let's find out about the output resistance. Well, you need to zero all the sources, so you zero all of these, and you want to find what's the parallel combination here. Well, 8R with 8R gives you 4R, 4 and 4 gives you 2, 2 and 2 gives you 1, 1 and 1 gives you half. So that's R over 2. And you multiply the two, and you'll see the exact action. So you can see the output is, in fact, in this form. And this is exactly what the most significant bit is multiplied by 8. The one after, multiplied by 4, 2, and 1. And you see the DAC operations. Very simple, right? Without really writing equation. I mean, we're writing equations, but there's different ways of writing equations that make life much easier. Let me now go to a little bit more complicated circuit. This is a quiz question on my exam usually. First time, they've seen the diff pair, they know how to solve the diff pair and find the voltage gain, but I just zero one of these so they can't use differential or half circuit, make the zero, and I have V in here, and I say find Vs. Find the voltage of this. And if you imagine, you could go ahead and draw the small signal model for these transistors, write KVL, KCL, and solve it, but life is going to be hell, very difficult. Why do you do this? When you can short it to ground. Okay, let's just do this. If I short this to ground, you don't see all of these guys go away because remember, there's no source in this half of the circuit and you're grounding it. So all of these go away and you just have this. And this is Vn, right? The short circuit current is GM times Vn. But of course you have RO of this and RD, so there's a voltage divider. But you can see that easily and you can write I short circuit is this. What about R equivalent? Well, you need to ground this Vn. So if I ground this here, looking it up, this was one of the library elements. This is a resistor. We already recognize it. This is a resistor. We already recognize it. This is a resistor. We already recognize it. So you have three resistors in parallel. You put them together and you multiply. And you get the Vs, as opposed to writing KVL and KCL. Again, I have nothing against KVL and KCL. I just like to avoid them if I could, and I see it more immediate, right? Okay, now I'm going to apply this to this last topic that I have, and that is flip voltage follower. I'm going to start with a simple voltage follower that, again, you've all seen. I promise you this is going to be a third-year undergrad, so I assume you've seen it. So we have a simple voltage follower. In this case, I'm using an NMOS transistor with a bias current, and I'm using a capacitive load. If I want to look at this and analyze it to find out what's the voltage gain, a small signal, I need to first get rid of this IB. I need to zero it. I need to zero this. And this becomes the equivalent circuit for a small signal, right, or an AC. So I need to analyze this. And I need to find out what is V out in terms of V in. Again, you can write KVL, KCL, but I prefer to short circuit and multiply. So I short this to ground. And if I short circuit, I don't see the load, of course. That's great. But what I see is that this is essentially a transistor, and this is the definition of the short circuit transconductance. I'm shorting this, and I'm looking at transconductance. So this is GM. This ratio is GM, and that's what's shown here. If I want to look at the output here, again, I don't consider the load because the load is going to be put back later. So looking into this, what do I see? This was one of the library elements, and this was RO in parallel with, this should be 1 over GME, my apologies. So it's 1 over GME in parallel with RO. And now you multiply these two, and you get this ratio. Now, if you assume that GME is larger than 1 over RO, which typically is, then you get GM over GME. You get a ratio that is approximately 1, maybe 0.8, and that's what we expect from a good voltage follower, right? And the question is always is that, yes, you have a small output impedance, and that is desired for a buffer or for a voltage follower, but how can I have it smaller? How can I reduce the output impedance here a bit more without changing the voltage follower ratio? I want to keep GM over GME, but I want to reduce the output resistance. And immediately you should note that if you want to keep the same voltage at the output, but you want to reduce this output impedance, then you need to increase its short circuit current. And you need to think of a way to increase short circuit current by the same amount that you want to reduce the output resistance. And that happens through the circuit referenced here is flip voltage follower. So instead of having the current source at the bottom of this transistor, you put it at the top and use a secondary transistor here. What is interesting about this circuit is that if you apply a voltage here, this current, I guess I should go back here. If you look at here, the current that you provide as a bias current is not just biasing the transistor, it's also providing the current that the load needs. So whenever the load is changing voltage and requires a different current, your bias current changes here, and that is changing the VGS of this transistor, and hence the action of voltage following is not doing as well as you want it to be. Once you go here, let's see what happens. You apply a voltage here, but then the IB is always fixed through M1, and I will show you in the next slide that the current for CL is really supplied or taken by this M2, and so this transistor remains as the voltage following action, perfect voltage following action, versus M2 that is actually supplying the current that you need so that you can maintain the voltage. So the action of voltage following and current supplying used to be happening by the same transistor, and now they're separated. And again, this is the subject of one article here that I want to mention. So let's analyze this using the techniques, circuit intuitions, and see what happens. So what I want to do is find out what is the, first of all, the voltage gain of the circuit. To find the voltage gain of the previous circuit, I got rid of this current source at the top, right? And I want to use short circuit times output resistance. So first, short circuit. How does this circuit do in terms of short circuit compared to the simple voltage follower? If I short this to ground, interestingly, I can actually take this and turn it into this. You see, this input voltage goes to M1, and this is short to ground, so that's the same as this, right? But the drain of M1 goes to the gate of M2. So I have it to the gate of M2, and I have M2, and that's short circuit current. So you can immediately see what's happening here. You have the voltage, and you had the short circuit current immediately before, because you had to short here. Now you have a voltage gain here, which is GMRO from here to here. Then you use the GM. So essentially, your short circuit current now is multiplied by GMRO. Before it was just GM. Now it's GMRO, which is typically, let's say, 10 times GM. So you increase them by a factor of 10. Our expectation is that, therefore, the output impedance should go down by the same factor. And let's see if that is true. So I want to find out what's the output impedance. Again, I apply a voltage source here, and I want to measure the current. I realize immediately that the I here is 0. Why is the I 0? Because it ends up being the gate of a transistor, which is open circuit. So there's no current here, only current here, except that when you look at this, the same as what I said about the previous case, when you apply a voltage here, it gets multiplied by 1 plus GME-RO and shows up here. So you multiply your voltage, and then you measure the current. And that is going to amplify this, and then you can see that I need to do this in two steps. First, I need to find out what is this current. To find this current, I need to find this voltage. To find this voltage, I use short circuit approach again. I short this to ground here first with this Vx. I measure this short circuit. I measure the output impedance of this node, and it will become RO, because then I need to ground this. So it become RO, and I multiply, I get this voltage. I go here, multiply by GM, I get I2, and I write it here, and you'll find out the R out in this case become exactly what you had before, but divided by GM RO. So what is interesting is that the output resistance came down by 1 over GM RO. The short circuit current went up by it. When you multiply, you get the same result as before. So for this, you have GM over GME, but this was GM times 1 over GME. For this one is also GM over GME. I don't know what happened here. Oh, this should be one line. But essentially GM multiplied by GMRO, and the output resistance reduced by GMRO. So this is going to help you with this concept that I know what is happening here, from here to here, not just equations, but what is underlying principle that makes this work. There are many more circuit intuitions articles. I think there are 37 of them, and I just covered some of them. So I thought I would just do a bit of advertising for the remaining ones if you're interested in this type of treatment of circuits. I have one article that just talks about negative resistance, and I show how easy it is to understand and appreciate negative resistance. It's really nothing complicated. Then I talk about switch capacitors, but I call it capacitor as a resistor. This was really the topic that I learned when I was a grad student, but then I learned that undergrads can enjoy it and they can benefit from it. So I wrote this article. So in fact, I went back to Maxwell. Maxwell was the one who came up with this, believe it or not. And then find his original article. In fact, if you look at the picture that I showed you, the 3 pages of Maxwell's treatise, the book that he wrote many years ago, and he talked about this. He was the inventor of this. And then we used it in circuit. So we use capacitors to build resistors. This is very important for us because capacitors are much cheaper to build in integrated circuits compared to resistors. And then I have fun with circles because I call it reinventing the wheel, the fact that we're dealing with sine and cosine, and there are many things in engineering, whether you're talking about oscillation in LC or elsewhere, we're always dealing with circles, and to understand that circle is very important, so I wrote an article on this. A random walk in a ring is quite interesting. You have 3 inverters. This goes into the domain of Kofi's talk, that he's going to talk about random movements and random fluctuations and process and mismatches. What happens to them? It's interesting that if you put 3 inverters that you want it to be identical, to have the same delay, they have some excess delay that is random. And when you do this, it becomes like a random walk, that you're throwing a dice as you walk. And this is what's happening inside a ring. And I hope you will enjoy that as well. And then the latest one that I just submitted 2 weeks ago is about Telegan's theorem. Again, one theorem that is probably deeply rooted in the first year of circuit theory. And then you thought that was just interesting. But then you will find the connections. And I'm planning to write the next one on reciprocity theorem, which I find fascinating. And this will take another hour to explain why is that so fascinating. In summary, what I said was that innovations in circuits is usually tied to our circuit intuition. So do not be shy about asking simple questions because you want to make things simple, because that is when you actually understand, and that leads you to innovation. So do not be afraid to say, I do not understand it. Don't worry. Probably your prof doesn't understand it either. But together, you can come up with that understanding, and then you can leap forward. And in fact, this is true for most of the graduate students. The topic that we work with graduate students sometimes is just as new to us than the graduate student. But we may have a bit more intuition, and that intuition helps them build the next innovation in that area. I also mentioned that intuitions help us feel at home with the circuit. Analogies are one way to reduce the barrier to understanding. And as I mentioned, water analogies is one case. use superposition principle, Thevenin and Norton equivalent circuit to navigate your way through the node. And I think the last one that I want you to remember from this talk is short circuit a node, measure the current, and multiply by equivalent resistance. I'd like to acknowledge members of my group. I'd like to acknowledge my undergraduate students who asked me these tough questions and forced me to come up with intuitions. And I'd like to thank the readers of Circuit Intuitions articles for great support and suggestions. And I'd like to thank you for being here today. These are some more resources. SSCS President John Long mentioned already, but I just want to mention that in Solid State Circuit magazine, in addition to Circuit Intuitions, there's a circuit for all seasons, now called Analog Mind, written by Behzad Rezavi, and Chris Mangelsdorf is writing about Shop Talk. These are all tutorial type, so you can all enjoy them, and please go and take a look at them. There's a YouTube channel of Solid State Circuit Society. This YouTube channel actually has a lot of great videos for you, and in fact, the Circuit Insights from ESSCIRC 2022 and 2023 are also on that website. You can take a look. And of course, there's a resource center that is for members only, so please do become a member. Thank you very much.
Now we have time for a Q&A session, so please ask questions. Maybe while you're thinking about the questions, okay, I will start, all right? So my very first question, Ali, is as follows. Was there a case when you actually was not developing intuition, like was not able to develop an intuition about the circuit? So, or maybe some complex circuit that you had an intuition and it actually happened to be wrong?
Okay, so these are two questions. I think there's a great question. I should confess, the reason why I thanked all my undergraduates is because they forced me to come up with simple explanation. Perhaps they've seen me being able to do it on certain cases, and they think, well, I should be able to do it on anything. So whenever they run into a problem, they come and ask me, well, what's the intuition behind it? Why is it working the way it is? And it's not that it's obviously I have it in my mind, I have to think about it. But I found that when I do, usually you have a solution. And again, if I want to just share a secret with you, this reciprocity concept that I mentioned at the end, it's been on my mind for a month. And it's amazing. And I've come up very close to it, but I don't have the final answer yet, but I'm sure I will get it by the time I need to write the article, and you will see it. It's just that, some of these take time. So if you find something, I think my advice is that do not give up. If you don't understand something, you can fool yourself to say, yeah, I understand it because the equation says so, so I'm done, right? Or to put it on your to-do list and say, I need to understand it. And then next time you go to a conference, you see Kofi, you go say, hi, I have a question for you, right? You ask Kofi. or you ask, well, because you have a lot of intuitions, Kofi. Or you go to people that you know. I mean, these are great topics of conversation. You're not expecting them to take out the book and write equations, right? You can just ask them, I've seen this concept, but I don't understand it. Can you explain it to me? And I think that will create great conversation, and you will have a lot of understanding coming out of it. And hopefully, you're helping people like Kofi and I to be forced to think of that intuition, because we need to have this handy to discuss this. So I think the second question you asked was if I was wrong on intuition.
Yeah.
I think this is very important because it's easy actually to make the wrong intuition, because in your effort to make things easy, sometimes you make it easier than it should be, and then things can go wrong. So remember, analogies, for example, have a limit of how far you can go, right? I used the analogy of water versus charge, and believe it or not, when I was looking at my own presentation this morning, I thought, oh, there is a difference though. And then I could find also the differences. So that puts the limit of how far these analogies can go. But hopefully, the analogies will help you go through a certain point and then get the understanding. And afterwards, it becomes so second nature to you that if somebody asks you to explain how you fill up a glass of water, you explain it with a capacitor because that's easier for you. So that is the process typically.
All right.
So feel free to ask any questions. There's no, as I said, I would love simple questions. So feel free to ask any questions that you may have. Yes?
I was really interested about your topic about negative resistance.
Yes.
Could you please talk a bit more about it?
Yeah, so negative resistance is not really an odd concept. It's just that if you apply a voltage, usually to a positive resistor, you expect the current to go inside, right? You put a voltage, positive voltage, current goes inside. Now, with transistors, it's easy. You get the current, you mirror it back to go that way. It's negative resistance, right? That's the intuition. You are satisfied? Perfect. Next question. Next question. You still read that article. There's a lot more into it than just that, okay? Yes?
Sure. If someone wants to answer the question.
Yeah, it would be great to use the microphone. Thank you.
Microphone.
Thank you. Yeah. I don't need a microphone, but you may need, yeah. Oh, recording, of course. Yeah, I should speak to the microphone too. Okay. Go ahead. Yeah, please go ahead.
No,
Go ahead.
I just want to know if you have. Oh, okay, sure. I was wondering, have you ever had one of your students ask about or suggest about a simpler way to look at a subject you had already published about in your Circuit Intuitions magazine? Maybe a simpler way to look at a subject that you hadn't thought before or anything like that?
Absolutely, all the time. I think as number of people that are in this room, probably at least, there are intuitions that are related to every one of these topics. It's just that you don't share them often. So when you go and ask someone, you can say, I have a different perspective. I'm sure you can find other ways of doing it. I'm sure if you go and look on Google it, you find a lot of other intuitions. And by no means, that's just only what I think as what I felt was interesting. But it doesn't mean that this is the only one. By no means. There are many, and yes, there's been many times where I have students, I probably don't want to name that person, but there's a person who is now a prof at MIT. And when I was teaching her in my undergrad course, I was talking about Miller's theorem. I've written 3 articles on Miller's theorem, but I'd like to give credit to that person. So when I was talking about Miller's theorem, you know Miller's theorem is that you have a resistor that is connected between a node, a voltage V, and another node that has minus A times V, let's say minus 10V. And that resistor could be made equivalent to 2 resistors that go from those nodes to ground. So instead of going from input to output, you become 2 resistors that go from the respective input and output to ground. And you know, I was doing this before, the way I was taught, and I didn't think about the intuition. But then this person offered an intuition that, is this the same as this? And when I thought about it, I thought, absolutely. And I just used that from then on to prove. And some of those intuitions, there's a good reason why I thank all my past undergraduate students, because a lot of these intuitions actually came from them, and I should really give them credit. Great question. Thank you. Other questions? Yes? You want to use the microphone, we were told? Yeah. Thank you.
Yes, my name is Erwin. I have a question regarding the limit, where you put the limit for your intuition. For example, for the Philip voltage follower, you didn't consider the effect of the current source on top, and then we assume that the M1 doesn't have any current, and we know that that node will affect on the many parameters, including the gain and then stability of the system. So normally, how do you define the limit for making it simple?
Okay. So first of all, the reason why I eliminated this current source at the top was not an approximation. That is exactly how you should do this if you want to analyze a circuit for small signal analysis. You get rid of the DC sources, and that was a DC source. But maybe what you're implying is that I assume that is ideal source. You don't have to assume it's ideal source. You can imagine that there's a resistance that only makes things a little bit different, but I didn't want to make it, those are unnecessary for understanding. So this is the process. You need to simplify to get close to it. And once you get it, you say, the rest doesn't matter. The rest is just, I don't want to say noise, but the rest is something that is cluttering your mind and you don't see it. So first thing you do is that you get a complicated circuit, you see what is really doing the work. And I find that in many of the circuits, it's the short circuit current and the output resistance that is doing the work. And if you do this, for example, this circuit, you can analyze it using feedback. It's far more complicated. Of course, I can use feedback for another hand-waving approach, but if you got to write the equation, you need to understand feedback. I didn't bring it here because short circuit is enough. It shows you what's going on. So, you know, when you're trying to give analogies, analogies is not meant to include all the details. Analogies are going to give you what is important. And I think that's what I emphasize. Thank you. Other questions? Yes. Microphone here, please. Yeah.
Who has the microphone?
Hello. I would like to ask about the example you showed, the problem with charging the resistor,
Right.
the power loss, and the solution would be to ramp the supply. Is this really done practically? I can imagine that the problem just shifts to the circuit that ramps the supply. This ramping VDD.
So this is the one you're talking about?
Yes.
The circuit? So what I suggest is that if you can devise a circuit that could have a ramp-up voltage, and what you're asking is that whether there's energy associated with this circuit that needs to do ramp-up, correct?
Yes, yes.
Yes, there is some into it, but if you design the circuit carefully, and this has been shown, that you do not lose half of the energy, you lose a lot less. So
Okay.
at the end, again, this is go back to the previous question, how far does it go in your analogies and your method? This is a known approach that's called adiabatic circuit, and people used it in the 80s to show that the circuit, for certain applications when you don't need speed. As soon as you need speed, then you'll go back to the problem. How do I ramp this up quickly without losing energy or without doing any damaging to the rest of efficiency in the circuit? Yes, that's the limit. Yeah.
Okay, thank you.
Thank you. Other questions? Okay, if not, I guess we're ready to go to the next talk. Thank you very much, everyone.